Yeah, welcome everyone for cloud computing and big data. We have our lecture 2 today, the second part of it. And in the first part, we learned really machine learning fundamentals, very basics when we start with a linear perception model. It's a model that stands the test of time in a way, if you want. It's one of the earliest machine learning models existing, but it captures the essence of machine learning from data. Admittedly, in part 1, we had a very simple problem. We call that linear separable data. So 2 data sets of 2 classes where you can easily make a decision boundary through. Unfortunately, I already have to tell you, if you have your industry projects, it will not look like this, right? Hence, advanced machine learning algorithms can deal with this, right? There are different algorithms which go much far beyond what the perceptron can do. And basically can then deal with, basically this kind of linear separable data sets. We go the first steps now in advancing a little bit when we had, let's say, the last time, just a very, let's say, linear learning model, linear in weights. So then we want to advance a little bit with something called logistic regression now. And by this, we continue a little bit with the CRISP-DM model in context so that you get this by heart. So again, for the industry project you do, I recommend that you structured it along that way in your simple report that you have to do for it, and also for the way how you work and make your notes and so on. So it's a very practical advice. And I did several master theses already on it, and which actually deal exactly with these steps. And it's quite a, let's say, industry proven mechanism of how to deal with data. The modeling is sometimes data mining in the literature. If you look up the CRISP-DM more, they will talk a lot about data mining, hence CRISP-DM, data mining. But you can nicely use it for machine learning as well. And as I said, it's some of the slides, there's a significant overlap. For instance, some clustering algorithms considered to be data mining, but DBScan already goes to some other areas. However, now when we go back to our ideas of having more application examples, and then also gradually with this showing you why then the cloud's becoming more and more interesting, right? So we have something today like Google Colab. Some of you know Google Colab probably from other courses or so. It's, let's say, a very simple mechanism of the cloud where you can have a GPU. But then we go quickly in the next area of Spark because Google Colab doesn't scale, right? You can just have one GPU or one TPU, and you don't even which GPU. And what we're talking about is we want to scale with multiple GPUs or multiple services. Hence, Apache Spark, the technology we will also end up today and then introduce in lecture 3. I talked to you that lecture 2 and 3 are sort of, closely combined. Is then the idea of scaling, and this means really leaving the Google Colab, power, and really have in theory, limitless, scalability with Apache Spark. You can add more and more workers and so on and so on. We will talk about this. Now, to go a bit from the flowers example that you had, again, so get it in your mind, the 3 steps, why you want to do machine learning. So the idea is you believe in a pattern, and here you have the application example of Chicago food inspections as an example, right? So there's a big report from someone investigated this. And I don't know if you have been in the US sometimes, but there are real restaurants that have sometimes C and B and A quality, and in New York, even D or so. And I was wondering why you want to eat at a restaurant with D quality, but sometimes there are long lines in front of it. So this is really happening in US. It's quite interesting. And here you would basically determine, is there a pattern that if the people have lots of words in it, and bad words probably, so the kitchen is unclean and whatever, can you have a, let's say, machine learning mechanism that, would predict this food inspection will probably fail or basically would, be satisfied. And, you can imagine this is an example again that there's no basically formula for it. Right, this is basically handwritten. There's some reports about it, maybe some ratings, how clean is the kitchen, but there's no mathematical physics formula about it. Hence, this will be something what you will inspect and will look at. Just to give you a sneak preview, really also for the next couple of lectures. And here the machine learning example would be again, can you categorize and find from these inputs of the data that existing from this food inspection data, these restaurants that will probably fail the inspection or basically will pass the inspection. So this is a bit loaded also, you will see, because then the data might be not directly linearly separable. So it would be kind of mixed interesting values in it, just to give you a kind of practical application problem. So then the next steps when you have this would be immediately these things that we had already established in the first lecture. I bring it now again into the practice, right, of thinking about the steps you need now in terms of using cloud computing. And there's lots of flexibility in this. Of course, we have many different cloud vendors. You learned them already, AWS, for instance, MS Azure, Google Cloud, Proc, and you name it, there are even the specialized ones. And usually would go that way when your laptop is not making it anymore, right? Or Google Colab is maybe, an example now that we want to go through later. But still, when you think about your laptop, you will be at some point at the end with your data sets. Hence, the first step maybe to Google Colab is useful. I'm not paid by Google, but it's a good service. So it's just, not really scaling, but it's still a good system to have. And when you want to scale, then you basically use something called, a cloud provider. And then you have to look for something, for instance, like here, Apache Spark clusters, right? So this is a particular way of using it in scale, which is called big data analytics. And as I said, also in the course, I put this now a bit earlier in the course than later. So hence, you don't know much about Apache Spark yet. We will see how that materializes in lecture 3. We talk then about Apache Spark much more in detail, why it's scaling, and also contrasted to Google Colab, why it's not scaling. So, and it's always similar steps, right? You always would check a subscription model. We will see that when you go to AWS. Do you have a student subscription, pay as you go, credit card swiping, and so on. So this is all what the cloud vendors have something in common with different financial models. We will come to this also during the course. And Hardy Insight is, for instance, one service you would pick here because it has a whole, let's say, open source system ecosystem around it. So Apache Spark essentially stands for not only one big data technology, but a whole ecosystem around it. We will talk about it much more because you can imagine we need, firstly, algorithms that are able to be parallel computed. Major difference to, let's say, Google Colab and others, right? We need something which can be working in parallel, really scalable. And that's just what the HD Insight and Apache Spark runtime enables us. And the ML library of it, it has parallel algorithms to deal with it. And this is a big distinction. Then the second, of course, you can imagine machine learning is learning from data. So we need data sets maybe out of an SQL engine, of so-called, table stores, column stores, NoSQL, as we call that. Have you used that maybe already in computer science or so? NoSQL stores, they're becoming more popular, some of you. So hence, there's a whole ecosystem around it of this Apache Spark, of lots of open source projects, which enables us, doing this. There's lots of data and machine learning libraries and so on. But I don't want to take drag the attention away. But if you go to Microsoft Azure now, you have this basically service available. And the benefit you would have there, and I'm not paid by Microsoft, just saying it's one of the services you could use. It has all these different templates where you have all the different versions of these open source projects already nicely combined, that they work with each other. Because if you do your own cloud at home, in the cellar on your own system, you have to make sure that, basically the HBase you have works nicely with the real engine of Apache Spark, works nicely with Apache Hive, another one. And so basically you have different open source projects in different versions that all need to play nicely together. And then you want to have nice things like Jupyter Notebooks connecting, right? Jupyter Notebooks, I think the majority of you knew last time, right? This nice way of accessing that you also know from Google Colab. So hence, that is now the first move of thinking, I want to go to the cloud because everything is so nicely, conveniently already working together, right? If you do this your own, with a project of open source, I had this done once with Advania and created it on their own cloud, 20 or whatever open source projects to deal with this in the right versions at the right time together is already significant work to work on. Hence, this is already a time saver if you just go there as a company and say, well, let's use Apache Spark and HD Insight. And we have this already in lecture 3 again, lecture 3.1, you see that you click the different versions and get more an understanding of this. Then you start up sort of a Jupyter Notebook usually, or Google Colab, right? Some way of accessing it. You will create a PySpark kernel. That's then the runtime behind it. From there, you can do different things. And then also this captures essentially then the idea of going to scalability or going local. And we also come to that. So the Spark session will be important. Everything is triggered from it. And we will learn this again in lecture 3 much more than today. And then you can do your crisp DM steps. You start, with loading data, inspect the data, hence data understanding, maybe data preparation. You delete some attributes. If you remember from the flower, we deleted some attributes or some classes even. Maybe they don't have representative numbers in classes. So hence your work starts then with a Spark session. And then there will be some point in time where you search a modeling step in this crisp DM, if you remember, where you would choose and say, well, what algorithm I want to use. Is it linear regression, logistic regression, support vector machines? Although a parallel support vector machine is not in Spark, I tell you that already. But random forests, let's say different decision trees that you can use quite nicely also in Apache Spark to make it scalable. Hence, this is all a process again, right? Again, it's not the one and only solution. We have this problem of Chicago food inspection. Let's throw that on and it works. Hence, you have to massage the data, and the idea of the next couple of lectures and your assignment there, assignment 2, is basically something where you learn exactly these steps. And then also that machine learning is essentially not really just throwing an algorithm to it. At the end, there are lots of evaluation mechanisms. There are different F1 scores and so on. We come to a couple of them at the end of today. So basically, this is something which we will always modify, this couple of 7 steps. And the problem usually remains what you see on the top, the scikit-learn, also on your little laptop or Anaconda, and all of these are usually at the end. And Azure is one of the specific one we will deal with. So now by starting, however, a little bit, let's say, back to the bottom line, right? Because you don't know so much about Spark yet. So we do a very, let's say, easy introduction on this, on another application, come back to these when we have Apache Spark established in lecture 3, right? So we focus a little bit on the machine learning point now, but we already use some aspects of Spark, which will be more explained in lecture 3. That's why they're both quite connected. So this example I have for you now that you also will experience in practice is basically then these bank deposits, right? So it's nothing special. You have certain properties, probably in all the different people that you have as customers of a bank, a musician, a scientist, or a businessman, just to have 3. And of course, there are many more. They have some certain, let's say, attributes which makes them either a saver, so want to have term deposits in the bank, or not, right? So this is something where we think when we know people, and some people in Germany know from Stuttgart, right? We call them the Schwaben. They are good for saving money, right? There's something in this area, every German knows they save a lot. So there's something in the attributes that makes them a saving person or not. So that we believe there's a pattern, hence we check this. Second, okay, again for you, when your boss comes in, do machine learning, please. You say, okay, let's check if there's a mathematical formula on this. To the best of our knowledge, if you correct me if I'm wrong, there's probably not any formula that can just look at people and say you're a saver, right? So it's also not existing. But we want to develop something similar to it with machine learning. And the third one is then, of course, the idea, is there data existing? And here we are lucky to have something from Kaggle. So this is now not the data set or the data repository I mentioned from the flower, right? The UCI data set. I think some of you maybe even know Kaggle. If not, it's worth to look. There's lots of data sets already prepared. If you want to learn about machine learning, it's quite nice to experiment a bit with the Kaggle data sets. Quite of them are, let's say, already a bit more nicer prepared than you would have really natural and live data. So let's say classes which have almost no representatives are gone, are basically outsampled, and some things like that. However, so it's an example that you have from Kaggle, and we can basically model this and understand now the business, what we want to do, hence a crisp DM in context. And feel free to raise your hand if you don't follow. We go one step deeper now with logistic regression, optimization, and so on. Then we would say, okay, we learned what we just had on a couple of slides before, but now we change the story just to see that this blueprint that you have of accessing the cloud is very, let's say, interchangeable, but the same principle remains. So we would say, okay, we have the bank and assume, okay, it's too slow runtime, we want to use a cloud. So we check the subscription. And if you go now, for instance, and say, well, I want to use a Google Colab and see, and several of you have already used the system, you see essentially it's free. For some of you, I would even recommend, if you do the machine learning course, So to use a premium, I think it's not expensive. It's like $9, I think, or something. Then you get a better, let's say, availability of the resources. But essentially, this is a sort of subscription again, right? In much more advanced clouds like AWS, Google Cloud, and so on. Not Google Colab, Google Cloud and Google Colab as a small difference you will notice, and also MS Azure. Of course, the subscription is much more expensive, right, than Google Colab, because then it also depends on how many GPUs you use, maybe 4 or 10. Don't worry, here in the course, we don't charge you, right? This is, of course, clear that we also provide you with the necessary credits for it. Then similar steps that we had before, we want to use Apache Spark to be scalable, right? So then really have, let's say, big data sets. If the bank data comes, more and more, we want to have a Jupyter notebook. If you remember, Google Colab a little bit looks like a Jupyter notebook. It has a sort of feeling for it. So we kind of use this. And then the same steps come again. You create the Spark session and so on. And that's what we're going to do now in this example in detail, step by step, so that you get your first practical view on it. And the same things apply with CrisDM, as you will see, and then do evaluation later. So hence, this is something we will come to basically with the Google Colab thing. There's just one big problem with it. You need to have a Google account, right? So in this sense, it's not a problem, maybe in some regard, but please let me know. We have every now and then people that don't like to have a Google account, then we will find another solution for it. But otherwise, the service is quite interesting. And when we start with this and Apache Spark, let's say from a higher level perspective, you have now the steps I was alluding to. We prepare now basically the package by having Spark essentially with Java and all the necessary underlying technology installed. Something what you can use is, pip install and so on. And then we have essentially here Spark unpressed. And so this is all things which you have to do to make your environment right to use Spark. When you go now basically to professional cloud vendors like MS Azure, the HD Insight service, this is all already there, right? These steps you don't need to do. This is just because Google Colab is sort of a very, let's say, fundamental cloud service for beginners and education, so that you don't, have all the different services you need already there, and you have to install a lot. But if you go to Google, Prog or AWS, all these different services around Spark and also the different open source packages, right? I talked about the data, storages, and so on, will be also available there. Still, we have to do this basically to get the Spark environment right. And again, lecture 3 will be explaining some of the similar elements. Here we see also that we basically have this Find Spark. Can we create sort of the basically Spark session in the end? And you need to know a little bit about Python, but I think that's sort of obvious in the course. And again, you don't need to have to program anything in the course, just follow the source code a little bit, where we then have several points. You also see one trick, essentially, that we have there a local master. In other words, we don't have really a big Apache cluster, right? And this is now one thing of this Google Colab we will understand better in lecture 3 and practical lecture 3.1 when we use a real cloud. Right, the Google Colab now is basically just one resource you have, and you cannot be doing something like this, right? So basically, like this picture alludes to. But this is our goal. However, it can do the same technology on top and basically have a local master and workers. We will talk about this, and make it as if we would work with a big Spark cluster. Hence, it is our first step to the cloud to have already remote computing. That is for many people something they never did before. They mostly work on their own, cluster or computer. Hence, this is already a first step. But when you then look in MS Azure, when we look in HD Insight, you will see we can steer the number of workers to really get to a real scalable solutions. And this is essentially what I'm talking about, the scalability of adding or removing more and more computing capacity. You can't do this with Google Colab. Right, you just ask for one GPU, one TPU, that's it. Hence, it's sort of a little bit of fake if you want, just to get to know a little bit Spark and how it works with PySpark. Then we have one data file that will be also available to you when we have the assignment, the bank CSV, right, that you can now look in, has all the data and the features we want to now look at and want to learn from. And we can nicely load that up. I mean, the majority of you know that you can upload data. If it's not big data, where comes the next limitation of this tool, right? We cannot have, let's say, terabytes uploaded via a browser. Hence, this is still digestible data for the first steps of your experience. Then we go into the step 4, as I mentioned. Now we have the subscription, we have the, the PySpark session on, so we have something to grab on. So that's important, Spark. That's our tool. We learn more about it in lecture 3 and a couple of things here today. And there are a couple of helper tools around it. One is a data frame from Spark, but some of you maybe know Pandas for data. Pandas, Python, beautiful. You learned this in Computer Science 101 already, or these days? Pandas? No, but it's very popular. I like that. It's good. You see in the second part, this is also used, right? So it has a much more beautiful interface and data frames and so on. And what you also expect now is basically coming back now to our CRISP model, which I also want to bring you to heart, is really the first step now, data understanding. Machine learning makes no sense if you don't have any idea about the data, right? You have to know your data. You don't need to know your data by heart, every single line, but you have to know something, for instance, what features are there? You see here quite when we, explain a person, what, could be interesting features. Age, obviously, we can imagine this has an impact on saving patterns. Then, what type of education maybe, then we have maybe a different loan statistics, or housing or no housing can also mean savings or no, because you basically want to get your house quickly owned. So you see, obviously, there are several attributes, we call them, like the petal width, petal length of the flowers. That is now exactly the same idea, attributes in the person, it's just a different application. So what of these might be interesting? There are a couple of them that seems to be a bit nonsense, so day and month. So this doesn't give us any information, apparently. 5th of May, okay. What should that be? So we maybe think about this already in our head and would say, okay, that makes no sense. However, one important point is there as well, and this makes it supervised learning. And this is the last line there, which is again now this idea from the Iris setosa and Iris virginica, right? So we had the class in the flowers, and exactly here we have also the class if they have deposit or not, binary, right? Hence, we can learn from the data the bank has. Obviously, it has data from previous customers that already are supervised learning models possible to use because we have this guiding output Y that we need. So there's some people in the past have deposit, some people not. So we learn from this, and we have all the features available, which is beautiful now for applying the supervised learning approaches. And this gives us a data understanding phase. So we know, okay, it's supervised. We have a label. We found something which is a guiding label. If you don't have that, you can still do something called clustering. You can do other unsupervised mechanisms. And today it's actually good chances with, let's say, quite big machine learning models, but they would be also not necessarily working with this little data set here, right? This is also something which is based more in machine learning theory, the law of large numbers and statistical learning theory. You need, a sort of balance, the data you have and the machine learning power and parameters like transformers needs to be equal or basically at the same level, right? If you have this bank data, which is almost no data, but you want to have a transformer model, which has lots of parameters, that doesn't work, right? So this is something which statistical learning theory, so state in his course, I think there you should learn these things. Not here. However, for us, it's important now to understand click in the data understanding phase. We have guided outputs Y. And the rest is basically just using, Python a little bit. You will do that yourself in the assignment. Hence, you will also, get more the grip of it. Then I talk a lot about this pandas and data frames. Now, interesting could be in this data understanding phase still to group. One important thing for classification usually is class balance, right? For instance, remote sensing, when we do satellite data, land cover, we have maybe 40, 50 classes. Is it trees? Is it this type of tree or is it type of corn? We have lots of interesting problems. But some of the classes have just 16 or, while others have 1,000 of, basically representatives in the class. Hence, these would be things where we usually have to drop this class because you have just not enough data to learn from, right? Hence, it's a first click again. So here you say, okay, we have deposit and not deposit. is almost the same level, right? So the class amount of those that deposit and those not is similar. When there would be someone having, in this problem now 10 that did a deposit, but the rest, like 10,000 almost did no deposit, there's nothing to learn from. The machine learning would fail because we have no, or basically would have a class bias if you want, also basically failing this problem. You can then, of course, basically get a kind of sub features or get an amount of data that is more similar. You can drop some if you want to make it similar, but this is already one of the important points, again, the class balance. Now, when we think about features, this is one of the interesting things is that here, this line is a bit complicated. The interesting thing is that for the mathematical model, we don't need to describe it so beautifully with age, balance, and then having already a loan or not loan housing. Basically, we have lots of mathematical models, and they can deal with it in mathematical values. Hence, there's no point of saying age or something. We need to know that, of course, to interpret it. But here we create a feature vector out of these, essentially, that we can then use essentially out of this much more easier. And with this have so-called data pipelines, which play a role in using it for training and later on for testing. Other elements we have here is, of course, summary statistics, which are important, like the min-max values and so on. Also, again, data understanding would be important. And you see also that maybe some of these data, like month or day, apparently would be having not much value as to tell, right? What's the entry of this? So hence we would do something called feature selection and, remove these two features out before we now basically create this nice feature vector in the next slide. But this also means we have the next step in CRISP, right? So we go from the data understanding phase now to something we call the data preparation phase. The data preparation phase means we change the data set, we make it more convenient for the machine learning model. We basically do something with the data, we modify it. And you see here now we have this data set that we have there. And for the data preparation, we now basically do this kind of trick I said for the mathematical convenience. We have rather an index basically here, that you have this one hot encoding of a very large feature vector that you create instead of keeping all of these different data, right? So this is one step what you could do for mathematical convenience, that you have just one value that is hot encoding, basically the values of all of these different elements. And we just pick some of these columns, as I said, that maybe make more interesting, for us to look at. And this would be, let's say, job and marital status, and education and so on. So with this, you basically, have this data preparation phase. You put that now into a machine learning model would be the next, and you have a sort of nice feature vector. But it also captures away the message that PySpark and Spark and all of these data analytics engines give you a lot of technologies and tools to massage the data, to work on the data, to index data, transpose data sometimes. So lots of different elements to really prepare these data sets for machine learning. And one hot encoding is one of that, right? This will be coming incredibly often if you do machine learning to make, let's say, out of a problem that is really not, let's say, more like a normal, relational database table sort of thing, a much more compact version to analyze and to work with machine learning models. And by this, you basically have then essentially this label that you have there, which captures now the top basically created our deposit, basically yes or no, the guided label. We just basically renamed this for our convenience. But the key point is now the second feature you see that we created ourselves. We call that feature engineering, right? So we engineered our own feature based on the others, but it makes it much more compact to have now this long feature vector instead of all these different ones. You're with me so far again? I know it's getting a bit more complicated, like the first part. That's the idea, moving towards machine learning, because usually you massage, as we call the data, quite heavily before you ever touch a machine learning algorithm. Good, by having done so, data preparation, the idea is now to have a so-called pipeline. And the pipeline is important for you to think now, and this is really something what you learn in industry, is you have the same problem, right? When new data arrives from perhaps another department in a relational database, it will always be the case that they give you data, which is a table, right? With mature status, education, the same old data that you now actually feature engineered, that you looked at, that you understand, that you dropped some. So what you want to establish is a pipeline that when new data comes, this is always happening, no matter if you train a new system. This is the first step, right? Training to have a machine learning model, or you use it for inference later, just basically for daily life. You want to have the same massaging of the data, because if you put the other data in for a machine learning model that, for instance, doesn't care about months and day, then it's stupid data and cannot be understood, right? You have basically this two usage models of this machine learning model. You want to train it in the beginning, put the same features in. Once it's trained, it's lying there, and then you put it, deploy it in the bank, and other people will use it, but they need to have the same massaging of the data happening, right? The same feature vector, the same dropping of months, day. And with this, you have a kind of pipeline that always should be working on the data. And there, Apache Spark, as you see here on the top slide, is also giving you lots of helper tools, where you essentially see that we have this selected column label features that we created basically as the columns we work on. And this gives you another feature of a combined feature set that maybe is really giving us, let's say, a strong expression out for the machine learning model. We will have this also in lecture 3 again, so lecture 3.1. So don't worry if you don't follow completely with everything. When we now look on the initial data analysis and data preparation, we have something that looks like this, right? This is maybe now better to understand. We have this label, deposit, yes and no. For mathematical convenience, we have set basically 1 and 0. Then we have this combined features from all of the different columns. And then, of course, the typical rest of the columns. So then they have some pandas, basically commands here to show you this top 5. And now the first thing starts with the Apache Spark cluster. We want to train the model, right? So the pipeline is used to train the model. For this, we have the training set and the test set load in. It's in the first place. And basically by using this, we have then, something nicely also from Spark called the ML library, where we have logistic regression, right, that we want to use. So hence another machine learning algorithm we want to fit with its features and with this label, and we learn in 10 iterations. So this is one parameter you can steer. And then you fit this model with a training set. You don't use a test set, right? Just a training set, you have splitted it. And then you get some, data. So basically the coefficients of this linear learning model, right? Similar like we had with the flowers, right? These W's we trained existing, and you can show a little bit there. And going from the modeling step, then slowly over to the evaluation step. So when you do logistic regression, just in short, and usually it would be almost one lecture, maybe in a university, you do nothing else that we did basically with the sign function with the flowers, if you remember from the W transpose X or the dot product. But instead of having the hypothesis set being the sign, so +1 or -1, we squeeze everything in the so-called logistic function. So put it between 0 and 1, making it a probability expression instead of a real value. Hence, we lose a little bit this real value element. By doing so, we have a probability if it then would be class 0 or class 1. Right? So this is basically the key essence of this logistic regression. Again, I brought you also a YouTube video if you can have a longer look into it. And the other aspect into it is that we use now something called optimization. There's an error function or a loss function, as it is sometimes called, that you see here, where we can always have the point-wise error measure because it's supervised, right? I can always use essentially the machine learning model as we have here done here and see the Y is not fitting as we should. So we have to change the weights again. And to change the weights again is a basically minimization of error problem, which brings us to a more complicated topic called optimization, right? So we have a space to look at. And this is now something where really, stochastic gradient descent comes in. Again, maybe how many people of you have gradient descent already heard? Quite a big fraction, right? So this is something where you deal essentially with this error function, this pointwise error, and then can basically take the gradient and go down the error slope. So this is something which, basically should be looked at much more deeper if you're in a proper machine learning course. We do this here in a very short manner, because again, it would take a whole, basically university lecture usually to go to. But I brought you also some, let's say, visualization, a little bit how you can imagine this is working. So by evaluating always the error, you can then have a function plotting the error and take the derivative of the, let's say, slowest, or basically the lowest slope. So by this, you go the lowest slope of error again and again down. By doing this iteratively is this gradient descent, right? The gradient, if you remember from a line that we have, showing us in which direction we go. And the hopefully element is that you reach something called the global minimum of error, right? Of the error space. And basically again and again take the derivative until you satisfied, hopefully in a global minimum. The trouble is you maybe sometimes are in the, let's say, local minimum. To deal with this is one very interesting parameter called the learning rate, where you can steer how much you go faster, or let's say with less pace downhill, and the steps you take. So hence it's a quite advanced topic where we come back to in hyperparameter optimization, how you pick the learning rate. Because if you pick it unwisely, you will always end up in, let's say, local minima, and with this have not the best solution you could have in machine learning. And again, I would say for some of you that maybe not are so keen in gradient descent yet, I would recommend to look into this a little bit deeper. It's, however, not a prerequisite in this course to understand it to the detail, right? But if you maybe look again on some elements, you will see it's actually not so hard to understand. And I guess Dane and the machine learning course has also more, let's say, material around it if you're interested. Now, then you have this model evaluation. You would say the area under rock curve, for instance, is a good indicator. There are several other ones, but all of that is now the interesting thing, is also supported by the engine. So all of these evaluation mechanisms are basically able to be used in this kind of Python environment. And with this have also the chance of seeing, is your model good enough or not? Or maybe you want to retrain, right? And do something more. And you want to use it then maybe also with unseen data. So now we use a test set out of our pocket that we throw in the corner that we never used to do a proper evaluation to basically what we say fake our out of sample performance, right? So this is something what we never touched in training, and this is important in machine learning to do so. Otherwise, you have an optimistic bias inside, and the machine learning model would be much more higher, reporting 99% when you learn from the training and test set as well. So keep the test set separate, using it then, and then the real evaluation will basically come through. And there are different ones like F measure and so on that we will revisit also in the evaluation during your assignment. So this will be one part of it to explain and basically also describe it a bit more. So much for today in this, let's say, introduction. You have now the opportunity, of course, then to use this pipeline again and again, do some differences in terms of, the training. You can have an iteration of 20. And these are, of course, you can imagine assignment points. So you should play around a little bit with this when you work with this, and not forgetting lecture 3, where we'll come back to similar elements and where you learn more and more and understand a little bit then more these elements. And by doing so, you will get an understanding of those people that actually have a deposit or not, as it is suggested here, and then are ready for those that are not in the training or in the test set, right? So this would be then getting future customers of the bank, right? That's why we do it. When the, let's say, area under the ROC curve is good enough. And in order to get to the best parameters and to really, work with the data, there's elements also where we have this, this grid here for cross-validation, also something where you want to play with in the assignment, because this is also now where we, use the data set multiple times, again and again, and where high performance computing, cloud computing also can make a big difference, right? It's very computing intensive. If you do, for instance, one-fold cross-validation, it's the most best you can do, but on the other hand, very time consuming. So the rule of thumb is 10-fold. But you see also here that people, try this with different parameters. And this will be also a little bit part of the assignment. And we come actually back in lecture 14 about it as well. So hence, lots of points to this logistic regression model, although it's one of the most simplest learning models again, right? Wait until you basically see in deep learning transformer models or autoencoders or things we do really in research, right? I have seen the question, 1 minute. And then we basically can say, even with the simplest model, like logistic regression, you have already the learning rate. One parameter the human steers is already a problem, right? So hence we have to do it systematically in lecture 14 and many others to choose from, where you then have the idea of to understand what are the parameters to use when you want to tune it to make it better, the model. That's it. And I come to the question in a moment. I just give you this a little bit as another tool in the cloud, right? SageMaker. I don't know if you have heard from it. Some of you, maybe also AutoGluon or so is a similar tool. You have heard from it? Yeah. Okay, good. So question before we stop. Well, if I capture the question right, is how much basically the algorithm parameters depend on the data size and the data itself, and how much and how it reacts. Yeah. So, I mean, it depends a bit on the data, to be saying, right? I mean, obviously, it should be similar data from the same probability distribution. If you put completely different data to it, let's say you have Netflix ratings and you put the ratings of a complete different engine, chances are that the accuracy is totally disturbed, right? Because it not gave rays from the same probability distribution. We come to this. That's why we don't do function approximation, although it looks a bit like this. But in machine learning, we do noise around it. Hence, we call it probabilistic approximate learning, because we cannot learn a function. And in our data, we have the same ratings for different inputs. So it would be not a function, right? If the same inputs, different output is not a function. Hence, in machine learning, we go one step more and put the probabilistic assumptions to it. And with this comes a data point. If the data stays in the same region of data, the size, volume, attributes, accuracy levels will follow, right? Other points, when you change, however, the parameters, just one spot in learning rate from 0.1 to 0.15 could make an extreme difference. Could be meaning that you do this gradient descent and you basically get lost in the minimum, which is local, instead of having maybe with the learning rate, so the hops you do a bit higher and you jump over the minimum, which is local, and then you have the global, and then suddenly less error and your accuracy will go up. So there are different points, and lecture 14 will be all about this exactly, right? To see that a human cannot do all of these different examples, but we have systematics in cloud computing and HPC how to do this and pick this systematically to find the best values. But of course, this is a computing footprint to have. But good question, yeah. Hence, there are lots of hiccups in machine learning. It's not that easy, but I hope you had a little bit of glimpse now what machine learning is. If you didn't understood all of it, don't worry about it. Not a requirement of the course. You know, we come back to this and be in lecture 3, practical lecture 3.1, your assignment 2, etc., etc. Any final question? Yeah. Okay, so it's an interesting question, class, about visualization. So data inspection, data understanding of data which is high dimensional. Actually, there are some mechanisms. We will have one, I think, even in lecture 3.1, if I remember correctly, but it's possible. Support vector machines are, for instance, a very good example in this, where they basically take you to a high level feature space. But the support vectors are in sample quantities, right? So basically, in other words, that give rise to a nonlinear decision boundaries, the support vectors, you can project that on the real data and have another understanding of a high dimensional data set and where the decision boundary is. But that is absolutely not obvious. So there are different mechanisms for doing it. And it usually projects a lot on lower space, obviously for us humans, right? Because we cannot think in 10D. Of course, but you know exactly, I've seen it in the bank data, it starts already with lots of attributes where this may be necessary and helpful to do so. And we will come to some mechanisms later in the course. All right. Any other question? Maybe to the online audience? Any questions? Going once? Twice? Okay, if that's not the case, then thank you very much. We continue with lecture 3 and the industry project on Thursday. Remember, time to choose and look at the SMEs. Finally, we want to start next week really with the real work. So thank you very much for today, and we continue with lecture 3 next time.